doing some things.
I only have one participant, it says. That's me, just hanging out by myself.
Now I should be able to join it now that it's done. 72649.
Yeah, right here. We're just waiting for Derek to get live feed from within the classroom here.
Yeah.
Don't worry. Still not seeing. This is going to appear on the video.
D-man.
Jedi Master.
Dinkle donkle. Oh, I don't know. Heck yeah, he's in.
I see that we have Dinkle Dinkle Little Star joining us. I'm going to share my screen, which is going to be. All right, so now, Derek, you should see these slides on your screen. Is that right?
Yeah.
Okay. All right. One of the things, so we've already used the plot command to plot data out of a file, and we saw that we can plot data from different columns. We can have multiple columns in our data file, and we can plot data using either any combination of those columns. The other thing that we have the option of doing is actually doing a calculation with the column numbers, the column data, before it gets plotted. So a simple example would be if you wanted to plot the second column squared versus the first column, or if you wanted to plot the first column times the second column and also plot that against with a shift in the X direction. And the way that we do that is we use the using option again. The syntax is basically the same. The first thing, you're going to separate the first and second columns by colon, or by a colon. If you're going to do a calculation, though, you have to put the calculation in parentheses. So without parentheses, you can't use an expression. It's just going to be a column number. If you want to do a calculation, you put it in parentheses, and then you have to reference the column numbers with $signs in front of them. And you can do any Gnuplot expression in here. You could put a function in there. You could just put a single number in there if you wanted to. So if you download the sandbox for today, there should be a directory called data. And inside that directory, I've got a file that I'm going to plot here.
Which one?
I versus T. All right, so let's say that I've got a data file that contains current versus time. So this is maybe like a measurement that was taken in Phys 2 lab where you had a resistor and a capacitor in series with each other. You're discharging that capacitor, and you measured the current through the resistor as a function of time. So we see that we start off here at some initial current, and this bottom axis, let's say, is in seconds. So it takes several seconds, over a minute, for this current to drop down to almost zero. Now I'm going to plot the same current, but I'm also going to plot along with it the current squared. And if you remember, electrical power that's dissipated by a resistor is proportional to the current squared, right? It's I squared R. So this is going to give us a function that is proportional to the power that is being dissipated by the resistor. And I don't have to measure this power that's dissipated by the resistor. I measure the current, and I can calculate the power that's dissipated by the resistor. And then I could either calculate that and put it into my data file, or I could just use Gnuplot to calculate it directly. So this here, the purple line is my current as a function of time. And the green line then would be proportional to the power as a function of time that's dissipated. It would, of course, depend on the resistor, right? The size of the resistor. Well, let's assume that it's a 3 ohm resistor. So I've got a 3 ohm resistor that I'm using to measure this current. Although I guess the first thing I want to point out is what happens if you don't wrap this expression in parentheses. So if I forget these parentheses, I'm going to get a complaint about an undefined value. So anything that is not going to be just a column number has got to go inside of parentheses. So I'm going to plot the second column squared times 3. So that would be the power dissipated by a 3 ohm resistor. Apparently this capacitor is ginormous because the time constant is out here at 50, 60 seconds. If the resistance is only 3, then it's got to be a pretty large capacitor. But let's not worry about those details. This would be the power that's dissipated by a 3 ohm resistor if I have this current as a function of time running through it. So I got the green points, those are my powers. I got the purple points, those are my currents. You can see that these things it's not really smooth, right? There's a little bit of variation in that. That's because there's uncertainty in this measurement. So sometimes you measure a little high, sometimes you measure a little low. Sometimes I want to use an expression that really is just sort of long. In this case, it's not too bad. But the nice thing is that inside of these column transformations, I can actually use functions, Gnuplot functions. So let me just define a function called power. Power takes 2 parameters, the current and the resistance. And then I just write down how do I calculate power if I know what the current and the resistance is? It's just I times R. And now I can use that function to do my column transformation. Notice up here in the top right corner at the key, Gnuplot is putting in basically just the arguments to the plot command that were used to create each of these plots. So it's not necessarily clear from this key that I'm calculating power. So one nice thing about using functions would be that when it goes up into the key, you can sort of indicate what that function is. So now I have power up here. Okay, so this is power, which is a function of the second column, and the resistance of the resistor, which I have set at 3 here. Now you don't have to exit. I'm going to exit real quick. I just want to look at this file here. If you paid attention to, and if you haven't plotted, you'll notice that the first data point is not at 0. And it's actually a little bit late. So let's say Corey and Joey are performing the experiment. Joey connects the resistor, says, Corey, go. Corey's got the stopwatch, right? And Corey's like, oh, wait, what'd you say? Oh, and he starts it. It's a little bit late. So the first data point I have starts at time 3.5. Let's just replot this so that that first one is at time 0. So what I could do is I could go through this file and I could subtract 3.5 from every one of those things in the first column. We don't want to do that. There's 80 of them, so I don't want to have to adjust that. Instead, I'm just going to do the adjustment in Gnuplot. So let me open up Gnuplot again. Just thinking about having class at the Q. Wouldn't that be great if we could? What? Okay, go. All right, so what I've done here is I'm going to plot the current as a function of time. So instead of using 1 for the X value, I'm using $1 minus 3.5. So I'm subtracting 3.5 from every one of those data points in that first column. And then I'm plotting the same thing, but then I'm going to calculate power using the second column. Notice that I've been using this little shorthand that I mentioned where if you're going to plot data out of the same file, you don't have to keep giving the file name. You can just use empty quotes. Ooh, and I've got an undefined function power. That's because I closed and then reopened. So let me redefine that function real quick. This would be a really good reason to just write all of this into a script so that I don't have to recreate all of this work that I do. If I close Gnuplot, open it back up. So there's my power, and now I'm going to plot.
You have to do define it in the first plot. Yeah.
What was your question?
I answered it.
Well, I mean, in case it helps somebody else.
Well, you have to do that for both plots, right?
Oh, you mean the shift? Yeah. Yep, I've got the shift in the X value on both of the plots so that both of them will be shifted. Trying to see if Derek, are you still here? I only have one participant.
I left.
Oh, you left.
It was a little annoying hearing it
Oh yeah.
like a slight time delay in
You,
one ear.
you should have chat or DM'd me. You should have DM'd me on here.
I did.
I'm learning.
I said some stuff and I put in.
Oh, you did?
To the global chat.
Uh-huh.
Nothing bad though.
This is awesome. I'm so glad you
Worst lecture ever. Like anyone could even know that, Napoleon. All right, so there we go. We put, right click's not what I want. Put this on top. All right. Now, the nice thing is that you can also give the using option while doing a fit. All right, so we've already done fits. This is exponential decay. Let me just do an exponential decay fit to the current as a function of time. So I've just got an exponent here. This is e to the negative x over tau. So tau will be the time constant. Yes, there.
Guess who's back?
And A is going to be the amplitude, right? So we've done this, and I'm telling it to fit via the constants or the parameters A and tau. So I do this fit. I get a value for A and tau. So it looks like the value for A is almost 1.5. And if I look here, that's pretty close, right? It looks like it's getting almost up to 1.5. Notice that, so actually this is not 1.5. Oh. This is 1.25, but that is not, is that occurring at 0? So the plot that I have up right now is shifted. The data actually has that point at 3.5. So what the fit is doing is it's extrapolating up to the y-axis. So if I actually wanted to fit to this data, so I wanted to set my first data point to 0 and then do a fit that matched that data, I can use the using option in the fit command to do the exact same transformation before the data gets fit. So here is the data by itself plotted against the function that fits. Oh, I've got that. There we go. So let's look at this piece right up here. So the first point is at 3.5, but then if I go back to 0, right, the function is up at 1.5. So let's say I want to do the fit and the data, assuming that this first one is 0. I just use the using command. So that's what I've got loaded here. I'm going to plot the file. I'm going to subtract 3.5 from all of the data points again. That is no longer going to match the function that I just fit, because the function that I just fit is assuming that the first data point actually starts at 3.5. So I see the data shift from that function. I'm going to go back to auto scale this. So I see this shift. All right, so now let's redo a fit that actually matches the function that I want to, or the data that I want to plot. And the way that I do that is I just use the using option again. So here's my fit, exact same function that I had before, same data file. Now I'm going to change the X values before they go into the fit. And then I'm going to fit that via A and tau. So what I should see is this A, value of A is going to have to come down. Right? Should be smaller. Now I see A is 1.25. Tau is still around 20. Plot my data versus my function. Now it lines up pretty good. Just answering my chats. Hello, my name is CD. How can I help you? Get support live.
Oh, first you're gonna need to pay for this service.
Yes. All you need to do is
$500
purchase the instructor service fee.
Yeah.
All right, so let me plot the power now again. So that's I'm going to shift the data so that the first data point is at time t equals 0. And then I'm going to calculate the power from the second column by squaring the current, multiplying by 3. This is also going to be an exponential function. Right? If I square an exponential function, I get another exponential function. The decay rate changes, right? Because there's a 2 that goes up in the exponent. And then, of course, the peak, the initial, is going to change. So I'm going to do a fit. This time I'm going to use A2 and tau2 so that I don't overwrite the A and tau that I had in the previous case. And so I want to fit this exponential function to the power. And so I give it the name of the file, and then I calculate what the power is, and I shift it so that the time, the first data point is at time t equals 0. I do the fit. I get A2 is equal to 4.27, or excuse me, 4.7, and tau is equal to 10. So if you square an exponent, you get a multiplication factor of 2 in the exponent, right? The time constant is the part that's in the denominator. So I've got negative t over the time constant. So if I square that function, I now have negative 2 times t over the time constant, which means that the time constant for that function is going to be 1/2 the original time constant. And so I get a decay rate here that is 10. So the time constant for this decay is 10 seconds. And then I get a different value for the initial value. Plot my data versus my function. Now this is the kind of stuff, it's very nice to be able to open up Gnuplot and do this stuff interactively to just kind of get a feel for, like what the range on the data is going to be, if the data looks like it's correct. But when you start getting to where you're going to do a fit, and I'm doing these column transformations, before I do the fit, I'm going to put that into a script, and I'm going to develop that script by running Gnuplot. Edit the script, run Gnuplot. Edit script, run Gnuplot. All right. So that's how we do column transformations. Another useful feature, especially for us scientists, what was that?
I said I didn't do that. I already did.
You weren't able to do that? I'll go slower next time.
Yeah, I got stuck not being able to use the tau value because I missed where you defined it. And so,
Tau? Oh,
Yeah.
I didn't define that. I just did the
It
fit.
told me the tau wasn't acceptable.
I did it in the fit, so it automatically gets defined when
Okay.
you do the fit.
So I must have missed that.
So another feature that would be useful to us scientists would be error bars. And so Gnuplot has the ability, with Gnuplot 5 now, there's a really nice ability to do error bars in both the X direction and the Y direction. I've also mentioned that you can have Gnuplot take into account the X and Y error bars when it does a fit. I'm probably going to do that in a second Gnuplot module, right? Actually looking at the effect of error bars on your fit. But at least getting error bars onto your plot is relatively straightforward as well. And the nice thing is you can also use column transformations to do error bars. So when I want to put error bars on a graph, the plot command is going to require more than 2 columns. So normally I run the plot command. First column is the X point. Second column is the Y point. If I want an error bar, I have to have another number that indicates either the X error or the Y error or both. So if I look inside the file again that we were just plotting, I actually have 4 columns in this file. The first and second columns were the only ones that we were using in the previous example. The third column here, let's say, is the uncertainty in the time measurement. So you're doing a measurement every second, it's plus or minus a ½ second, let's say. The second one is the uncertainty in the current measurement. I'm using a voltmeter. Let's say it only goes to a 1/10 of or I guess I'd be using an ammeter, only goes to a 1/10 of an amp. So I have an uncertainty of a 1/10 of an amp in all of my current measurements. let's get those uncertainties onto the plot. So using the first and second column, that's the data that we've already been plotting. If I want to plot error bars, I use the with option. So this is kind of like with lines points. As I say with error bars. And that doesn't make any sense at all.
Yeah, why'd the graph change?
Why did the graph change? I'm telling it to use columns 1 and 2 with error bars. The with error bars option is going to make it look for 3 columns. And so if I force it to use just these 2 columns, it looks like it's plotting the first column versus the first column, right? That's why it's a straight line, 10, 10, 20, 20. And then it's using the second column for the error bars, I guess. Let's do this.
You put another semicolon in a 4, it fixes it.
Yeah, let's do I versus T using 1, 2, 3 with error bars. There we go. So now I see Y error bars.
I thought that the error that we were looking for was the 4th column.
That's exactly right. So the with error bars is going to just put error bars on the Y, on the in the Y direction. My error bars for the Y direction are actually in the 4th column. So using 1, 2, and 3 is not correct here. The 3rd column is my X error bars. So that's going to give me the same. So let me plot this function using 1, 2, and 4 with error bars now. And so now I see little 1/10 of an amp error bars put onto my data. If I wanted to just do the X error bars, I would use X error bars. But the X error is not in column 4, it's in column 3. So here would be error bars in the X direction. Plug in the
So like the Y error bar is the default.
Y error bars are the default. And you can specify specifically that you want Y error bars. If you do that, and then I can also do error bars in both directions if I say X, Y error bars. Now I need 4 columns of data. So this is going to be columns 1, 2, 3, and 4. And now I've got error bars in the X direction and the Y direction.
Ooh, man.
Now that is error bars that I specifically collected and put into my data file. In this case, the columns are the exact same, right? The column is 3 and 4 have the same number over and over and over again. That's because I directly estimated what the error in each one of those were, right? So I didn't do some sort of statistics. So if that's the case, I don't actually have to put the error bars for the X and the Y direction in the file. I can just list those in my plot. So let's say, again, that the uncertainty of time is a ½ second and the uncertainty in current is 1/10 of an amp. So in this case, I'm just using column transformation, but I'm just giving it a single number. So it's going to get the same number every time it goes to plot it. And I can reproduce that plot without putting those uncertainties into my plot. Now, if every line had a different uncertainty that I had to quantify, then yeah, I would have to put those into those 3rd and 4th columns so that I could plot the varying error bars for every point. But if I do this, then it's easy to change. If I say, oh, well, actually it was I've been saying 1/10, that was 100th of an amp. I thought I had 1/10 of an amp in there. It turns out I was using 100th of an amp. I need to put 0.1 in for the error. Now I can go back and change the uncertainty in the Y direction. You can also, this will also allow you to use like a relative uncertainty. Let's say I know that I've got 10% error in both the time and the current. Well, I can calculate what 10% of every time and every current is using this column transformation. So I'm going to do 0.1 times the first column and 0.1 times the second column. Now I see the uncertainty in the y direction is big here for these large currents. The uncertainty in the x direction is small because the time is small. As I go to the other end, now the uncertainty in the x direction gets large, the uncertainty in the y direction gets small. So if I know that I've got 5% uncertainty in all of my measurements, I just do a column transformation to calculate what 5% of the x or the y values are. See what else I got in here. That's not going to work. What else does it want to do? X, Y error bars, not enough columns. This one should work. There we go. Specify the uncertainty directly. Set it in the x direction. Set it for the x and y direction. So set it to static values in the x and the y direction. And then probably percentage. 10% error in the x direction, 10% error in the y direction. What was that? That's right.
Make sure we get it.
Nothing like beating that dead horse only to find that it hasn't remembered anything that you've said.
Honestly, just wait till we have a horse on it.
Yeah. It's
Hey,
like,
Clark.
didn't I repeat that like 10 times in class? And I told you you'd forget it?
That's why you watch the video at the same time, so it's being repeated twice over.
That's right.
Then you get it 4 times.
Yeah.
All right, I got one more example I want to do. Any car enthusiasts out there?
Card.
Car.
Card. Pitch man.
All right, if I go to that data file, I have a file called torque versus RPM. This is a torque curve. So this would be an engine or car, right? If you put it on the dyno wheel. Engine RPM in the left, in the first column, and then the torque output by the engine in the right column. So torque is a force divided by a radius there. It's basically when we do rotational mechanics, torque takes the place of force for causing accelerations that are rotations. So an engine produces some torque at a given RPM, and this is relatively straightforward to measure. You can measure this directly. So let's plot that, see what it looks like. And this is a pretty standard torque curve. I got this off of some example online. They were like rebuilding an old Chevy, 350 or something like that. Maybe it's a 427. And so at low RPM, right, 2,500 is pretty much idle for most car engines. At low RPM, I have some torque. As I rev the engine up, I get a torque increase. So the torque that it's producing goes up. And then as I keep revving, the torque goes down. Right, and I go up to 5,500, which is pretty high for most. Well, it's pretty high for V8 engines, right? That's like close to red line for a V8. You get a little 4-cylinder, and it's like 8,000 RPM. Those the Ford Mustangs had those little 4.6s that would do like 6,000 or 7,000 RPM. The Mazda, you guys know? Have you heard of the Wankel engine? It's that little model back there. So instead of it being like a regular piston engine, it's this engine that just rotates. It's like a triangular little thing that sort of rotates inside of the engine itself. Those apparently can do 10, 15,000 RPM. But this would be like a standard, Chevy small block, Chevy big block, good old days type stuff. All right, so what's the power? I'm going to plot the torque curve again with some uncertainty. I'm going to do a 0.05 uncertainty, which is basically so small that you can't even see. Did it actually put those on there? Oh, no, it did not put those on there because I have not plotted it with error bars. So let's do with X, Y error bars. There we go. So there's some uncertainty in my torque curve. Now, what is the power? The power, it turns out there's a formula that everybody uses, but it's basically a little bit of physics with some unit conversions. Torque is a force times some distance, right? If I have circular motion, I have a lever arm, I apply a force, take the cross product of those two, I get the torque. If this is a 90-degree angle, then it doesn't, then, you know, I get sine of 90 degrees, which is 1. So that's what torque is. Let's see here. Angular, so how fast it's spinning, that would be RPMs. RPM would be a unit for angular velocity, revolutions per minute. We typically use radian per second in our physics classes, but the angular velocity is equal to a linear velocity times r. So if this point is moving with some velocity v around the circle, I just take that velocity, actually I've got this backwards, that velocity divided by r gives me the angular velocity, right? And then power is related to force and distance. How do I calculate power if I have a linear force? Well, power is going to be the time derivative of work, which is going to be the time derivative of force times some distance traveled, right? If the force is constant, then it's just the time derivative of the distance traveled, which means it's just a force times a velocity. So power is force times velocity. Work or energy is force times distance. So if I go to calculate power here, force times velocity, I have torque divided by r times omega times r, which is just torque times omega. So it's actually the same. So force times velocity is power, torque times angular velocity is power. Both of those calculations give you power. Now, the units are going to be the thing that gives me this conversion factor. So the units that are used on automobile torque is foot-pounds. So 1 pound of force applied 1 foot away from the center is a foot-pound. In SI units, we would use Newton meters. 1 Newton of force applied 1 meter from the center. The unit used for power in automobiles is horsepower. Horsepower then will be related to watts. So a unit of 1 unit of, or a watt of power will be equal to some number of horsepower. I think that 1 watt of power is equal to 745 horsepower or something like that. All right, so if you do the unit conversion, you're going to take revolutions per minute multiplied by foot-pounds, and then you're going to unit convert that to horsepower. And when you do that, you're going to find that the power is equal to the torque times the angular velocity divided by 52. This then will be horsepower. This is in foot-pounds, and this is in revolutions per minute. So all I have to do to calculate the power then is take the torque value, multiply by RPM, and divide by 5252.
When a horsepower is 740 watt, 7 watt.
It's the opposite way?
Yeah.
So 1 horsepower is 740 something, 45 watts.
Yeah.
That's the amount of work that a horse can do in 1 second.
So watt's not all that much energy, but a horse can't do a full watt of power.
Made up by like tractor companies or something that would just for
I don't know. Lots of stuff. I think so. It's like,
Yeah.
how does this compare to a horse? This is like one horse.
It can pull as much as 2 horses.
I think they show this.
I assume by using horses.
Just the standard horse, of course.
They would just find out your standard. They would go to the horse store, buy a standard horse, and then go and measure how many trees it can pull.
All right, so here's my torque curve, and let's calculate the power curve then. So the power curve is going to be the same function I want to do power versus RPM, so I need to calculate the power. That's going to be the first column times the second column divided by 5252. All right, and so now I see, now the units on the left axis are not the same, right? The two curves are plotted on the same graph so that you can compare them, but they have different units. The units on the x-axis is going to be the same for both graphs. So let me put an X label on here. So X label, that's going to be angular velocity, and that's in RPM. And the Y label is torque. Oh man, torque's got a Q in it, right? Torque and power, which is foot-pounds and horsepower there. All right, so let's look at this curve. I'm going to do it with lines.
You could be with torque. My high school physics teacher would always pronounce it torque.
Torque.
Yeah.
All right, so I've got lines points on here. One thing that if you want to make sure, if you want to do all graphs as lines or lines points or points, you can actually set a setting to make all of the graphs plot with lines. And you're going to do set style data. So you're setting the style option. Subset of the style options would be data. So how do you want the style applied to your data? And I'm going to do lines points here. So now if I replot, I don't have to put with lines points on every one that I want. All right, so the purple one is torque and the green one is power. And so I see that they peak at different places. So I get the maximum torque, which is of course what the manufacturer is going to list, peak torque, peak power. Peak here is going to be, it looks like 508, so 508 foot-pounds. And then the peak power is over here at higher RPM, and that's going to be just shy of 400, so 397 horsepower. If you look at these torque curves, basically what you get, if you want high horsepower, you need your torque to be high at high RPM. So the fact that this torque peaks down here at 3,200 RPM, which is relatively low RPM, means that the power is going to peak out at around 400, which is not, I mean, 400 is a lot, but you know, it could be higher. You'll see if your torque curve peaks up here at the high RPMs, then you get much, much more horsepower. So you want torque, yes, but you want the torque to be in the high RPM range so that you can get a lot of horsepower out of it. And then there's always these discussions about whether or not you want high torque or high horsepower, because torque's what actually pulls, right? Torque is directly related to a force. So you need a lot of torque to like pull a trailer, for example. But you only need a lot of torque to pull a trailer from rest. If you want to pass somebody with a trailer, you need a lot of power. Right? If I'm doing 60 miles an hour and I want to accelerate to 70 miles an hour, that takes power, not torque. All right, that's all I got for Gnuplot this first round. We're going to pick up on, we're going to do data analysis. We're going to learn how to use pipes on the command line to do some data manipulation. Oh, I've been falling behind on my chat window here. What was your tau value?
That was quite a while ago. That was only, I put that on